Hi, AP Chemistry kids. So this week we're starting Unit 2, and we're going to spend this week and our and next week getting into 2-1 through 2-3. So that's 2-1, 2-2, and 2-3 on your visible learning objectives. So let's just check out what those are. Now, we're not going to spend much time on 2-1, or probably not at all, because it's the metric system. It's something that you should recall from Chemistry 1, so you need to go back and review that stuff. There are materials posted in Schoology, and you can check it out to review the metric system, but we're not going to spend a lot of time on that, or really any time. We're just going to jump right into mole calculations and stoichiometry. But hold on, let me just share that with you. All right. So, oops. So if you look at 2-1, it's the metric system, some significant digit stuff, how to calculate percent error. So that's all Chemistry 1 stuff. You really need to go back and review your Chemistry 1 notes if you still have them. And if not, then you probably need to come in and get some help at some point with all of these. All right. So we're going to talk about mole calculations and percent composition. So empirical molecular formulas. And then we're going to really focus on stoichiometry. And the real one that we want to hammer home this year is solution stoichiometry. So understanding what molarity is and how to use molarity as a conversion factor to convert from liters to moles or moles to liters. And so that's really something that we really need to understand. But hopefully, as we go through these different types of calculations, you'll feel comfortable with them. Hopefully, it'll be a lot of review, stuff that you already know how to do. You just needed a quick refresher on. Okay, so there are guided notes. So make sure you check out the materials posted in Schoology to get guided notes on the stoichiometry and solution stoichiometry PowerPoint. Okay, so that's what we're going to go over today. Stoichiometry we're going to go through pretty quickly, and then we're going to focus on solution stoichiometry. So again, there are guided notes posted in Schoology, so make sure you check those out. All right. So let's get into stoichiometry. Okay, and again, it's not just stoichiometry; it's also mole calculations. So understanding how to use the mole map and all that stuff is a good thing. All right. So again, also posted in Schoology is your mole map. So if you look at the Unit 2 supplements, that would be a good idea to check out. You have your mole map, so you can remember how to do all your mole calculations and all that good stuff. All right. So let's go ahead and jump into stoichiometry. All right, so stoichiometry is essentially calculations you do following a recipe. It's really our way to convert amount of one substance to amount of another substance. So maybe I give you the amount of water, and I want to know how much oxygen's in that water. Or maybe I give you a couple different reactants, and you have to determine how much product is going to be created. So if this much benzene burns in oxygen, how much CO2 is going to be produced? You're given the amount of one thing, you're asked to find the amount of a different thing. That's what stoichiometry is, okay? All right, so again, how do you know you have a stoichiometry problem? You're given the amount of one thing, you're asked to find something else, okay? And so once it is a stoichiometry problem, there's 4 steps you have to follow. You just follow the 4 steps. A lot of times the steps are already done for you, but if you follow those 4 steps, you're going to be in good shape, all right? So we could break stoichiometry down into 3 different types, but it's really just what recipe you're using and what measurements you're given that differentiate between the two. If you just follow your steps for stoic, there's 4 steps, then you're good to go, all right? So composition stoic, we do with a chemical formula, okay? And I'll show you an example of that. Reaction stoic we use with a balanced equation. And solution stoic is also with a balanced equation, or it could be composition stoic, but it's just using molarity and understanding molarity as a measurement. Okay, so let's talk about composition stoich. Okay, so in composition stoich, you're using a chemical formula like CO2 as your recipe. Okay, so this question is asking how many oxygen atoms are in a 15-liter sample of CO2 gas at STP. Okay, so I know it's stoichiometry and not just a normal mole calculation because they're asking for oxygen atoms, but they gave me CO2. So they gave me carbon dioxide, which is one substance. They're asking for oxygen atoms, which is a different substance. So I know it's stoichiometry. Okay, so I'm given the amount of one thing, I'm asked to find the amount of something else. All right. So this is the setup. This is what you would do. All right. But let's talk about what we're doing here, right? So the first thing I did was I took my liters of CO2 at standard temperature and pressure and I converted it to moles, right? That's just using your mole map, right? So dividing by 22.4 is going to give me moles of CO2. This right here is the stoichiometric step. This is using my recipe. I know based on this chemical equation, or sorry, chemical formula, there's 2 O's for every 1 C, right? So there's 2 moles of oxygen atoms for every 1 mole of CO2 molecules. So that's using my recipe. That's the conversion I needed. And I needed to know the chemical formula for CO2 in order to get that ratio. Okay, so that cancels out. And then I convert to my desired units. Just remember in AP chemistry, we use 6.022, but that's okay. All right, everyone hopefully you get the idea, you do the math, and you got it. So what were those steps, okay? So step 1 is know your recipe. You either have to have your balanced chemical equation or you have to have your chemical formula, all right? In that previous example case, we had our chemical formula, okay? Then what did we do? We took our given amount, we had 15 liters of CO2, and we converted it to moles. So step 2 is to take your given amount and convert it to moles. Sometimes it's already there, okay? Step 3 is following the recipe. So in our example, we knew that we had 2 oxygen atoms for every 1 CO2 molecule, and so that was us following the recipe. And then step 4 was convert to desired units. We had moles of oxygen atoms, but we wanted total oxygen atoms, so we multiplied by Avogadro's number to figure out the total oxygen atoms. So those are the 4 steps we follow, and it works every time. A lot of times, the recipe's given to you. Move to step 2. A lot of times, you're given moles. Move to step 3. Okay? And sometimes you might be asked for moles. So once you are given once you're asked for moles, then you don't have to do step 4 because you already have moles. Okay? All right. All right. So how many grams of hydrogen are found in an 18-gram sample of propane? So again, we have stoichiometry because I was given propane and I was asked for hydrogen. Okay? So step 1, know the recipe. So I have to know the formula for propane. They gave it to me there. All right. Take what I'm given, grams of propane, convert it to moles. How do I do that? I divide by the molar mass. Okay. The ratio of hydrogen to propane is 8:1. 8 hydrogens for every 1 propane. And then convert to desired units. I wanted to know grams of hydrogen. So I multiply by the molar mass of H. Notice this is an H2. It's H. So just 1.01. And that gives me how many grams of hydrogen are in that many grams of propane. Okay. All right. So again, now we move on to reaction stoichiometry. So now our recipe is a balanced chemical equation. And what we want to understand is the coefficients in our balanced equation are moles. And so those ratios are called the mole ratios. So the different mole ratios I can get from this balanced equation, I have 3 H's, I have 1 nitrogen, and I have 2 ammonias. The mole ratios I can get from that are, I could say 3 moles of H2 over 1 mole of N2, right? 3 over 1. Or I could flip that, I could say 1 over 3, okay? And so I'm not going to use all these ratios when I'm doing stoichiometry. I'm going to use, the one that's going to convert what I already have into what I'm looking for, okay? All right, so let's look at this question. How do we know it's stoichiometry? It asks how many grams of ammonia will be produced when this many grams of hydrogen react with excess nitrogen. Okay, great. So I'm given an amount of hydrogen. I'm asked to find the amount of ammonia. So I know it's stoichiometry. I'm going to follow my steps. So step one, know my recipe. So I got to have my balanced equation. So I have my recipe up here, okay? Step two, take what I'm given, 3.75 grams of hydrogen, convert it to moles. How do I do that? I divide by the molar mass of H2, okay? Step three, mole ratio, okay? Coefficient of what you're looking for goes on top. I wanted ammonia, so 2 moles of ammonia on top. The coefficient of what I already have goes on bottom, 3 moles of hydrogen on the bottom. Then step four, convert to desired units. If I just did this part, right, if I just did this divided by this times 2 over 3, that would give me moles of ammonia, but the question asked for mass. So now step four, convert to the mass from moles to mass of ammonia. So you multiply by the molar mass of ammonia, okay? All right, so again, know the recipe, take what you're given and convert it to moles. Use the recipe, find the mole ratio given the recipe, and then convert to desired units, okay? All right, so this question, what volume of oxygen is required to completely combust 38 grams of propane? Okay, so I have 38 grams of propane and I want to know what volume of oxygen is required. So again, what would we do? We'd have to know our recipe. So we have a combustion reaction. So we'd have propane plus oxygen yields CO2 plus H2O. We have to balance it, okay? And now that we have it balanced, that's our recipe. We move to step two. Take what I'm given, convert it to moles. I was given grams of propane. I convert it to moles of propane by dividing by propane's molar mass, okay? Now mole ratio step, it's asking about oxygen, so 5 goes on top. I have propane, so 1 goes on the bottom, 5-to-1 ratio, okay? That will give me moles of oxygen once I do all that math there, but the question asks for volume at STP. Oxygen's a gas at standard temperature and pressure, so how do I go from moles of a gas to volume? If I'm at STP, I multiply by 22.4. So step 4, convert to desired units, and I have my answer. Okay, 96.5 liters of oxygen. Okay. So here's another another stoichiometry problem. Okay, so how do we do it? Okay, we want to know what mass of iron, so we want to figure out how much Fe is required to make this much iron 3 oxide, assuming we have excess oxygen. Okay, so again, we're given the amount of rust, and we want to find the amount of iron. Okay, so we know it's stoichiometry, we follow our steps. So we'd have to say iron plus oxygen yields Fe2O3. We got to balance it, all right? Now that we have our balanced equation, which our recipe is, now we'll take what we're given, convert it to moles. So I would take my grams of rust, divide by the molar mass of rust, okay? The mole ratio of iron to rust is 4-to-2, so that's where I get 4/2 here. Okay, if you want to reduce it and go 2/1, you can, but you don't have to. And then multiply by the molar mass of the iron to get the desired units. In this case, we wanted to know what mass of iron. That's why we multiply by the molar mass there. Okay, so that's stoichiometry in a nutshell. It just takes practice, and the more practice you do, the better off you'll be. Now let's move on to solution stoich. All right, so we probably won't finish this on this lesson, but we're gonna try to get pretty far into it, all right? So in order to do solution stoich, you just have to understand how we measure a solution. So first, let's understand what a solution is. Now in chemistry, we're just gonna be talking about water-based solutions. So our solvent is gonna be water, and our solute is gonna be different compounds that dissolve in water, okay? So for instance, salt water, okay? If our solution is salt water, our solute is the NaCl, and our solvent is the water, okay? Water is going to be our solvent whenever we're doing solution stoichiometry, okay? So we're going to be talking about aqueous solutions, things dissolved in water, okay? So in order to do stoichiometry with solutions, we have to have a measurement of how concentrated they are, okay? And there's different ways to measure concentration, but our measurement of concentration is molarity. And molarity is equal to moles of the solute. So if we want to use salt water as our example, it's moles of the solute per liter of solution. So remember, it's not per liter of water, it's per liter of solution, which is going to be the volume of the solute and the solvent, the water and the salt, or whatever is dissolved. Okay, that's what molarity is equal to. Okay, if we want to make an equation out of it, molarity equals moles over liters. Moles of what? Whatever's dissolved, okay, over the volume of solution. And it has to be moles, not grams of the solute, and it has to be volume in liters, not milliliters, okay? All right, so the symbol for molarity is M, okay? But anytime you see M, you might want to remember that, well, what is M? It's moles per liter, okay? That's probably a better way to think about it, especially when we're talking about dimensional analysis and conversion factors, okay? So if you're told you have a sodium chloride solution is 1.0 M, the better way to think about that is 1 mole per liter. And really, the best way to think about it is 1 mole of NaCl for every 1 liter of solution. Okay, it's whatever this number is here goes with the solute. So if this was 2.8, that would be 2.8 moles of NaCl for every liter of solution. All right, that's the way to interpret it. All right. If you see the word molar, it just means molarity. Okay. All right. But when I ask you how concentrated something is, the measurement I want in return is molarity. Okay. There's other units of concentration that we may use down the line in this class, but it's very rare in AP chemistry. But another kind of popular measurement of concentration is similar in sound. It's molality versus molarity, but it's very similar, okay? All right. So find the molarity of a 3-liter solution that contains 6.8 grams. We have to understand, in order to find the molarity, we got to take the moles of the sodium chloride and divide it by liters. So we'd have to convert our grams of sodium chloride to moles, and once we had moles, we can divide by liters, boom, and we get our molarity. Okay. All right. So this one, they give us the molarity, and they give us the mass we want of our salt, and we want to know what volume to measure. So we're solving for the liters. Okay? We're solving for the liters. But let's talk about how we get there. All right? All right. So what I would do here is I would take my grams of calcium chloride that I'm trying to measure out with my solution, and I'd convert it to moles, so divide by the molar mass of calcium chloride. And then here I'm using molarity as a conversion factor, right? If it's, wrong slide. If it's that many moles per liter, you could say 1.3 moles over 1 liter, or you could say 1 liter over that many moles. So once I have moles, I can divide by the molarity, and that'll cancel out moles and give me liters. Okay? So moving forward, we want to think of this measurement here as 2 conversion factors. So if this is what you're given, this is how you interpret it. And you would use this conversion factor to cancel out liters and get moles of the solute. And you would use this to cancel out moles and get liters of the solution. Okay, so given this, you have these 2 conversion factors. And so, again, stoichiometry, a lot of stoichiometry is the better you understand dimensional analysis, the better you're going to be at stoichiometry, because that's essentially all it is. And you got to know where to get conversion factors from when you're doing dimensional analysis. So a really important thing for you moving forward in this course is understanding how molarity is a conversion factor. It converts liters of a solution to moles of the solute, or it converts moles of the solute to liters of the solution. Okay. Right. So how many grams of sodium chloride is in 25.6 milliliters of 1.60 molar solution? Okay. Well, I would take my volume, convert it to liters. Okay. Then liters times the molarity would give me moles, and then moles times the molar mass of the solute would give me the grams. Okay. So this right here is my molarity that was given to me as a conversion factor to cancel out liters and get moles. And then once I have moles times the molar mass to get grams. Okay. So solution stoic is the same thing. It's just we're dealing with molarity as a measurement instead of just grams or particles or volume of a gas at STP. So it's just a new measurement to deal with. Okay, but the steps for solution stoichiometry are the exact same. Okay, so this asks what mass of lead 2 chloride will precipitate if 15 milliliters of a 1.5 molar solution of lead nitrate is added to excess sodium chloride. So we know it's stoichiometry because we're given an amount of lead nitrate and we're asked to find the amount of lead chloride. So let's follow our steps. Okay, step 1, balance our equation. So we got a double replacement reaction going. Okay, sodium chloride and lead nitrate. The sodium switches places with the lead, so the lead's paired up with the chloride, and the sodium's paired up with the nitrate. We want to make sure we get the right formulas. And we were told that lead chloride precipitates. It's not very soluble. Make sure you review your solubility rules, but it's not very soluble. All right. So step 1, know our recipe, and it's really easy. It's a 1-to-1 ratio for lead chloride to lead nitrate, so that's good. Now we're going to take what we're given and convert it to moles. What was I given? I was given volume and molarity. So this should be your mantra this unit. Liters times molarity gives you moles. Just repeat that, repeat that, repeat that. Liters times molarity gives you moles. And that's what we have to do. Take what we're given and convert it to moles. Liters times molarity gives you moles. This was milliliters, so we got to convert it, 0.015 liters. So if I take my liters times the molarity, that'll give me moles, okay? And that's moles of lead nitrate. Now we go to our mole ratio. We follow the recipe, 1-to-1. 1 mole of lead chloride over 1 mole of lead nitrate, and then multiply by the molar mass of lead chloride, so we'd have to calculate that using our periodic table, and that'll give us our answer there. Okay? All right. Here's another example. Okay? All right, so in this case, we're using our molarity as a conversion factor in the last step. So a student wants 45 grams of silver chloride. So we're given 45 grams of silver chloride, and we want to know what volume of the silver nitrate solution should we use if we have excess sodium chloride. So we have a recipe, but now we're going to take 45 grams of silver chloride and divide it by the molar mass of silver chloride times the ratio 1-to-1. And then now we're taking moles of silver nitrate and dividing by its molarity to get liters. And we're using our molarity as a conversion factor here. That'll give us our liters, multiply that by 1,000, that'll be how many milliliters, if you wanted to know. But again, all solution stoichiometry is regular stoichiometry, just with molarity instead of other mole measurements, okay? So again, it just takes practice. I'll have another lesson later this week for those of you that are homesick on combustion analysis, but go ahead and get started on your 2-2, 2-3 assessments in Schoology, see how you do. And as always, if you have questions, please stop by during office hours.